In this video, we're going to talk about linear dependence and independence of a set of vectors. So our first definition is linear dependence of column vectors. So we have this set of vectors, and if we can find a scalar and multiply it by one of the vectors, so a different scalar for each vector, and that when I add that together I get 0, then we know that these are linearly dependent. The set is linearly dependent. Similarly, the only way I can do that if they're independent is that the only vector or the only scalars that work, alpha 1 through alpha n, is when it is the trivial set. So in other words, the only way I can get a linear combination to make it equal 0 of all of my vectors is if each one of my scalars is 0. So that is the linear independence. The thing to note here when we're talking about independence and dependence, at this moment we're talking about a set of vectors. So we're talking about linear independence, and we're talking about a set of vectors, or linear dependence, it is a set of vectors. It is not necessarily a system of equations, a linear system of equations. We're talking about vectors which are column vectors. And it's easy to take a set of vectors and an equal number of scalars, all 0, and form a linear combination that equals a 0 vector. But that isn't what we're saying here. So linear independence means the only way I do this scalar multiplication by each one of the vectors and get 0 is if all of my scalars are 0. So that's just something to note there. So if we're trying to determine whether or not this system is linear independent or dependent, then what I do is I take my vectors and I put them into a matrix. So 1, negative 2, 1, 2, negative 1, 3, 1, 5, and 0. And then I reduced row echelon form this matrix, and when I get done I end up with 1, 0, 0, 0, 1, 0, 0, 0, 1. And then because I was able to reduce row echelon form into this matrix, this tells me, because happens to be the identity matrix, that this tells me that these are linearly independent. Because the only way I'm going to get if this is my u1 vector, my u2 vector, my u3 vector, the only way I'm going to get alpha 1 times my u1 vector plus alpha 2 times my u2 vector plus alpha 3 times my u3 vector and equals 0 is if all of my alphas equal 0. That's the only way that's going to happen. Let's take a look at our next example here. Okay, so for my next example, again, I'm going to go ahead and put this into a matrix. So I get negative 1, 2, 4, and 2, 3, 3, negative 1, 3, 7, 3, negative 6, and 4. Reduced row echelon form, and I get the matrix 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. And here, because the only way that I'm going to get here's my U1, my U2, my U3. The only way I'm going to get alpha 1 U1 plus alpha 2 U2 plus alpha 3 U3 to equal the 0 vector is if it's the trivial solution where it is alpha 1, alpha 2, alpha 3 equals 0. And we know that because my number of pivots here, my R is equal to 3, and the number of columns I have is equal to 3. So my pivots equal my number of columns. So again, this one is linearly independent. This one is independent. Let's take a look at my next example here. So again, I'm going to throw these into a matrix. And so my matrix is 1, 2, negative 1, 0, 1, 3, 2, negative 1, 2, 2, 4, 4, negative 2, 2, 3, negative 1, 2, negative 1, negative 2, 0. Again, I'm going to do the reduced row echelon form, and I end up with this matrix 1, and then 1, 2, 3. Let me see, 1, 2, 3, 4 zeros, 0, 1, 1, 2, 3 zeros, 1, 1, oh, right there. We know right away because I'm starting to see non-pivot columns that I know that this is linear dependent. Again, my R happens to be 2. I have 2 pivot columns, but my N, the number of columns I have, is 4. So I know that these are linearly dependent, and I know from my last video when we're talking about the spanning sets that my alphas are going to be formed by my null space. So the null space, we'll call this A, we'll call this matrix A, is going to be equal to, well, I know from, let me just erase this, I know from this that my free variable is going to be that alpha sub 3 and also alpha sub 4. So when I start building my equation or my vectors here, so I know this is my first vector and it's coming from the coefficients of alpha 3. So I'm just going to say that's coming from the coefficients in alpha 3. And then my second vector here, which is z2, it's coming from the coefficients on alpha 4. It's not alpha 4. That vector is not called alpha 4 and alpha 3. It is actually z1 and z2. But anyways, so I'm going to go ahead and start building these 2 vectors. The coefficient for the first position, which would be my first column, my alpha 1, if you like, is going to be in terms of these 2. So alpha 1 is going to be in terms of this alpha 3 and alpha 4. So in this first position, I'm going to have -1 and -2. My second column is here, and it's going to be in terms of these 2 columns, these alpha 3 and alpha 4. So that's going to be -1 and 1. Alpha 3 was the free variable, so that's going to be 1 and 0. And alpha 4 was a free variable, so that's 0, 1. So these are my null space. These are my vectors z1 and z2. And what that tells me, because my null space is not empty, and that my number of rows, my number of pivots, number of pivots is 2. My number of columns is 4. I knew it was going to be linear dependent. And in fact, one of the ways that I can have that is that -1 U1 minus, it's U1, minus 1 U2 plus 1 U3 plus 0 U4 will give me the 0 vector. And I got all that information right here. Another way in which I can get the 0 vector is I can have -2 U1 plus 1 U2 plus 0 U3, and then plus 1 U4 will also give me the 0 vector. And this is my U1, U2, U3, and U4. So this set of vectors are linearly dependent, and I know that from here. Okay, so let's go ahead and take a look at this next theorem. My next theorem here is the linear independent vectors and homogeneous systems, and linear independent vectors R and N. So as we read through this is in particular 2 homogeneous systems. So I have a set of column vectors whose entries come from the complex numbers. M just tells us how many entries we're going to have. We can be in R, the real numbers. Complex is a larger number set, so we usually stay in complex. This is a set of vectors, and A is the M by N matrix that is built with these columns, as are the vectors in the set S. Then it is linearly independent if and only if the homogeneous system of the LS, remember this is for the linear system, built with the matrix A is and 0 being the homogeneous, what it's equal to, the constants if you will, as a unique solution. And similarly, I got linear independent vectors, R and N. Suppose that we have this set of vectors, again we're in CMM tells us how many entries we're going to have in our vectors, is a set of vectors, and MN is whose columns are the vectors. Let B be a matrix in a reduced row echelon form. Now, this has nothing to do with a system. So the second theorem is going to be just a set of vectors. This first theorem is in a homogeneous system of linear equations. This is in just a set of vectors. Then we know by just looking at it, that they're going to be linear independent if and only if the number of pivots equal the number of columns. So if I come back up here to my example here, my number of pivots were 2, but my columns were 4. So I didn't even have to go through all of this. If I would have known this linear, or this theorem, I could have told you right out of the gate that this was linear dependent based on that theorem. So let's take a look at this example. And they're asking us to determine by our previous theorem, just by inspection, whether or not we have dependence or independence. So once again, what I'm going to do is we're going to go ahead and put this into a matrix. So I have 2, 1, 3, negative 1, 2, 4, negative 2, 1, 3, 2, 10, negative 7, 0, 10, 4. Reduced row echelon form gives me the 1, 0, 0, 0. Let me see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then I have 0, 1, 0, 0, 0. My last column is negative 3, and I can stop right there because I can tell you that that is a non-pivot column. So my R is 2, 2 pivot columns. The number of columns I have is 3, and so we know since N is larger than R, we are dependent by my previous theorem. Okay, so that gives me this next theorem. It says, suppose that I have more vectors than I have entries. That's pretty much what it says. It has more vectors than I have entries in each vector. That tells me right out of the gate that it is linearly dependent. So if I take a look at this, the number of entries M is 3, but the number of vectors I have is 5. Because my 5 is larger than 3, then just by inspection, I know that this is dependent. Just because of the fact I have more entries, or I have more columns than I have entries in each vector. So no work has to be done there. The next theorem that I get that says, suppose A is a square matrix, then A is non-singular if and only if A is a linear independent set. What does this mean? Well, it means that if I can get to the identity matrix when I put it in reduced row echelon form, that means we are linearly independent. So if I take this vector, or this set of column vectors in this matrix, and I reduced row echelon form this matrix, and if I get the identity matrix, and I do with this particular example, of course I didn't write it that way, I know that this will be linear independent. So that should be a 1 right there. So we know that this is independent. So that theorem says if I have a square matrix, it is non-singular. In other words, I can reduce row into the identity matrix. I know I have a set of vectors that are linearly independent. Now let's take a look at the theorem here. The theorem of non-singular matrix equivalences, round 2. This kind of sums up everything for what we need. Is if A is non-singular, they're independent. A row reduces to the identity matrix, it means they're non-singular, they're independent. The null space of A contains only the zero vector, that means they're independent. And row reduces to the identity, it's non-singular. The linear system in which B has a unique system if and only if for every possible of B. So in other words, what I can do now for this part number 4, it says that basically if I can take the coefficient matrix, and it doesn't have to be a homogeneous system, if I can take the coefficient matrix and get it into the identity matrix, when I put it in row reduced echelon form, then I know that I'm going to have a unique solution for my system. And lastly, I'm linearly independent. My last theorem in this section is the theorem basis for the null set. Suppose A is an m by n matrix and B is row equivalent. In other words, I've done reduced row echelon form with R pivots. Then my D set, which is this D set, just as a reminder, is all the columns that are dependent. And my free set, these are all the columns that have the free variables, be the set of column indices where B does and does not respectively have pivot columns. We construct the n minus r vectors, so in other words, remember like we were doing before, the z1, z2. Then what we know is that null space becomes the spanning set, and that null space is linearly independent. So what are we going to do with that information? Well, what we're going to do is we're going to find a basis by taking our column vectors, put them into a matrix, row reduce it, and see whether or not we're going to get a basis. In this case, the basis will be the null set, and it will become my spanning set. So I'm going to take this example and I'm going to go ahead and put it into row echelon form. This matrix in row echelon form is 1, 0, 0, 0, 1, 0, 1, 1, 0, negative 2, 1, 0. This tells me that my number of pivots is 2. And I knew they were linear dependent. I knew that because I had more columns than I should have had. And my n is 4, so I knew that. My free variables happen here, which is the x3 and the x4. So my null space of A is going to be the vector set, and this is my z1, but remember this is coming from my x sub 3. They're all in terms of x sub 3. And then my other vector, and I know I should have two vectors in here. This one is my z sub 2, and it's in terms of 4. Okay, and then, so let's go ahead and start filling this out. So in my first position, in both vectors, it will be the coefficient on the x sub 3, which is this case negative 1, and then positive 2. So in my first position, it'll be negative 1 and positive 2. My second position here in my vectors will be the coefficients in reference to the x sub 2. And so that'll be a negative 1 and a negative 1. So negative 1, negative 1. My x sub 3 is the free variable, so we know that that's going to be 1 here and 0 here. My x sub 4 is a free variable, so that's 0, 1 in here. So I found the null space. What this tells me then is my spanning set is these vectors, z1, z2, which is equal to the negative 1, 1, 0, and 2, negative 1, 0, 1. What this tells me is that these are the only vectors that we need to produce every vector within the span. So this is my spanning set, and I get that from my previous theorem, and I also know that these are linearly independent of each other. So that's it for this section.